Okay, hello everybody, and welcome to the IET Northwest Midlands. And we have a very exciting speaker today. In fact, this is an incredible, almost an oversubscription of numbers of people. I think we had over 500 people registered for this event. So it's very exciting for us to be able to share this event with all of you. So I'll just introduce myself. My name's Sam Wayne. I'm the chair of the IET Northwest Midlands, and hopefully you've seen the holding slides there, and you've seen about some of the events that we have. Particularly, we have our Northwest Midlands local network, and we have a website, and on that website you can meet some of us and you can see our details, and you can also see details about our upcoming AGM. So if you are a member of the IET, and particularly if you're in the Northwest Midlands region, then we would absolutely welcome you to join us on our virtual AGM, which will be on the 26th of November at 6 o'clock. And of course, you're all welcome to, if you're interested in joining in on the committee, or you just want to come along and see what we're up to, that's absolutely fine. We always welcome people onto the committee. We've got a very dynamic and vibrant bunch of people in our committee, and an excellent set of events which will be starting in 2021. Whether they'll be running virtually or face-to-face, we don't know yet, but we do know that they will actually be running. So watch this space and stay with us on that. So just a bit of housekeeping. We have an excellent talk from Terklin, who I'll pass over to Amelia to introduce in a moment. So if you have questions, and I'm sure you will have questions along the way, you are all muted, but you can use the Q&A button. So if you wiggle your mouse, you'll see a Q&A button, and then you can ask your questions there. At the end of the presentation, we'll give Terklin a bit of a chance to have a bit of a breather, and then Amelia, my colleague in the committee, will then field the questions verbally to Terklin, who will then answer them verbally. And of course, you're welcome to add to the questions by text, and we'll just see how it goes from there. So that's how you ask the questions. There is also a chat box And feel free to use that. I will use that and send some links about the IET Northwest Midlands local network website. I'll put some links on of where you can download your CPD certificates. I'll put some links on about the AGM and how to contact your local committee if you're within the IET Northwest Midlands. So do check in on the chat. That would be fine. Feel free to use the chat box yourselves as well. That's always very interesting to do. So wonderful. It gives me great pleasure to pass on to my colleague. I'm pointing this way because on my Zoom, she's to my left. It's a bit like that, the squares, you know, the what you ask the questions. They did it on the Muppet Show. But we're not that. So I'll pass you over to Amelia, who will host the event from here, and have a fantastic evening. Thank you very much.
Thank you, Sam. Hello, everyone, and thank you for joining us tonight. My name is Emilia Kapfunde, and I'm a member of the committee in the local IET Northwest Midlands network. As Sam said, there will be some links shared on the chat box. So if you do want to go onto the local IET network Northwest Midlands, please feel free. You can find us there. You can find more information about the committee, what we do, and future events that are coming as well. Tonight, I have the pleasure of introducing Terklin Sinulingga. He is a senior bid manager at GE Grid Solutions here in UK. He's got more than 30 years experience in different areas of GE or former Alstom. From 3 different countries, Indonesia, France, and UK. His past experience have made him very interested in HVDC, and he's taken that interest a step further and written a book on VSC HVDC. So today he's joining us as the presenter of this event. He will be wearing the hat of an author. The contents of his presentation are from his book. They are not from GE. So he is looking at the general VSC HVDC technology. At this point, I will hand over to Terklin.
Thank you very much, Emmy. Yes. So my name Terklin Sinulingga. So today, I'm trying to share my experience for HVDC. Actually, HVDC here, I'm working in GE, but actually my interest is from academic view. So I have written 2 HVDC books. So I'm an author of VSC and Renewable Energy. And then the second one, LCC for power transmission. So if you see here, so this is the topic we want to discuss today, HVDC and renewable energy transmission. Actually, the book still in Indonesia. Now I'm translating this book to English. So once again, my presentation here, not related my company. This is purely based on my interest of HVDC. So what I have put it in my book here, actually based on the HVDC overall from academic point of view. So this is my first book. So we will have a presentation today, part of this book, and then maybe the second one will be in January because the topic quite hectic to put in one day. And then the next one, this is my second book. This is, if first one talking about HVDC, voltage source converter. And the second one about LCC. Again, this book is also still in Indonesian. I'm translating now to English. This topic will be, maybe will be discussed and also will be presented in next year as well. So there is a 1 or 2 more events for next year. First of all, to continue what we are doing today, half of this book. And then in March, maybe we are talking about the next one, talking about LCC book. So today, the topic regarding renewable energy. So if we see electrical background here, today what happened, the requirement to meet target for CO2 reduction. So what happened here, actually fossil will be used up. So the tendency, we will move from fossil fuel, become green energy, green electricity. What is green electricity? Green electricity is wind farm, geothermal, solar, and so on. So in the future, of course, there are so many renewable energy will be built, and then it will be transferred either through AC or DC. So the presentation content today, as I mentioned to you, we will have actually 6 chapters out of 11 chapters of my book. So the first will be today. We will talking about 6 topic. What is HVDC and AC technology, and then the next one VSC and configuration. And the next, number 3, we are talking about design and working concept. The 4th one, talking about layout. 5th, control system. And then the last one will be protection system. This is the one we want to review this evening, while we expect to have the other session for this for 29 January 2021. For January, the topic will cover renewable energy transmission, study engineering and performance, SVDC. Next one, talking about factory testing, field testing, and all warranty period. The number 10 will be economic comparison between AC and DC, and then the last one we discuss about a reference project. So today we are going to go to chapter 1. For chapter 1, actually, for electrical power, we can transfer either through AC and DC. While for DC, actually, we can transfer either using voltage source converter, VSC. This is my first book, my second book. And then the next one, line commutated converter. This is LCC book. This is the one we will discuss in March next year. So what is AC? AC actually interconnection between 2 systems, system A to system B. So what happened here when we are talking about AC, the voltage from system A, when we deliver to system B, the voltage should be same, and then should be synchron. And there is also one more requirement, the frequency should be same. Let's say if we have 50 Hertz here, we have to have the system B 50 Hertz. The same if we have 60 Hertz here, we should have 60 Hertz on the second one. We could not transfer the power if we have different frequency. And here we have limitation because very long transmission line at the end will be uneconomic, and also for the AC they have a very high losses, so very not good for to transfer with very high losses. In addition to this, if we have long transmission, the transmission tend to be asynchronous. And then the next one, when we are talking about green electricity, today what we see here, most of renewable, especially we are talking about bulk power, it's located in isolated area or located in offshore. If we are talking about offshore, we have problem for cable, where the cable actually they have a problem for charging current, meaning we cannot transfer the power for long time because the reactive power in the cable will be very high. So what happened here, we will go to SVDC. For SVDC, actually, this is the different from what we have for AC. If we want to transfer the power from system A to system B, we do not need the same voltage. The same here, we don't need to be synchronous because everything will be managed by valve here. In addition to this, there is no requirement for frequency because the frequency will be zero, transfer to zero, and then in in the end substation will be back to the requirement, whatever the frequency needed for the end substation. So in HVDC, sending substation, we call it rectifier, and then receiving substation, we call inverter, where actually here the process of HVDC actually here. So from AC, we transfer, we convert here to DC, and then will be transmitted through DC, and after end of substation will be transferred back to AC. So transmission here, when we are talking about transmission, we are talking about renewable. Renewable, we can see here, most of renewable today, especially if we are talking about Germany, for instance, most of so many offshore renewable energy built in that country. And also the good thing for VSC, we have a small footprint for this, so that's why we need only a small platform. And VSC also, they have a capability to have a black start operation. What is HVDC? Actually, HVDC talking about converter. Converter here not only used for high voltage part, for low voltage or medium voltage, converter also used in renewable energy for wind farm and solar panel. So actually, what we want to say here, when we transfer the power for wind farm or from solar panel, they also need converter. The last thing, we have a problem here. Because the technology development is very, very fast, actually there's a gap between the academic curriculum here with industry. Hence, actually, what I want to say here, we have to have a close academic relation between, close relation between academic and industry, but this academic can catch up whatever happened in the field today. So when we are talking about HVDC and AC, we are talking about comparison. Comparison can be from economic view, comparison between technical performance and impact of environment. So here, I just give one example, the economic view. The economic view here, we will discuss actually this session in the chapter 10, it will be January. But what I want to say here, for AC here, AC, the starting point, we have a very low cost because we don't have a substation quite cheap. But for AC, we have converter station. So that's why the initial cost quite expensive. But however, because DC, we need only less number of conductor, smaller tower, and then smaller right away. At the end, let's say like by rule of thumb, for 700 kilometers for overhead line, break-even cost between AC and DC can be reached. The same for cable, about 40 to 50 kilometers. But this is once again rule of thumb. This is really depend on parameter of power and also, mainly for the power. The more power we transfer, the less distance for break-even cost. So we will discuss more here in January, even for when we are talking about chapter 10. Here, I give comparison between AC and DC. If we see here, for AC, we have AC substation, but for DC, we have rectifier and inverter. For voltage, today we are talking about 1.2 kilovolt, but here for DC, we only have 1,000 kilovolt. This is mainly in China. And then for electricity system can be reached until 5 gig. But today for VSC, we can say only maximum 2 gig. And for transmission line here, we have maximum 2,000 because of reactive problem. But here we don't have limitation because we don't have reactive power in transmission line. For the tower here, we have big for AC, but for VSC, small tower. Right away, we have large, and here we have small because the tower and transmission number of conductors smaller. Active power control, we need additional equipment, but for VSC, we have default here. Reactive power, load dependent, while for VSC, producing and absorbing rectifier. So actually here, VSC, we can produce rectifier. For control, we need reactor, but here we have default technology. For power reversal, we can say it's same for both. For filter, no need for AC in case harmonic small. But if we generate more harmonic, we need filter. But for VSC, especially, we are talking about MMC configuration, we almost do not need AC filter. Multi-station, both for AC, VSC, and AC we can. And backstart for AC default technology in case our generator equipped with black start capability. If not, will not be working. However, for VSC, by default, we can do a black start capability. In terms of losses, will be big because we have more number of cable. But here we have a small number of cable, so that's why the losses will be small. Here we are talking about single line diagram. If we see here single line diagram and converter configuration, so here when we are talking about HVDC, we also still need AC substation. We need converter station with all associated equipment. And then in DC side, we also have a fault reactor, we have DC smoothing reactor, we have converter valve, and then it will be transmitted through overhead line at the end, and receiving end, we also have converter, we have AC substation, and then the same, we can transfer the power using AC voltage. So this is the main equipment here. We are talking about AC substation, pre-inserting resistor, grounding resistor, DC smoothing reactor, valve reactor, converter valve, and converter transformer. In terms of configuration for VSC, we have five types of configuration: symmetrical monopole, asymmetrical monopole, bipole, multi-terminal, and back-to-back. Let's see one by one. So for symmetrical monopole, we have two high voltage material. The voltage between positive and negative polarity will be same. So that's why we don't need. So that's why we have a balanced voltage in the converter station. And since we have two high voltage conductor, so all current return current using metallic return. So by this we do not need any, we don't have any problem for ground fault. There is the advantage of this. We have because we are using high voltage conductor. So at the end, the insulation will be very high. And also here, because we only have symmetrical monopole, so in case one cable or one conductor disturbance or problem with the electricity will be stopped. This is for symmetrical monopole. For asymmetrical monopole, we have two types, metallic return and ground return. For ground return here, metallic return here, if we see here, for metallic return, we need only one high voltage conductor, while for return part, we can use medium voltage. For this polarity, voltage polarity between positive and negative will not be same. So for this, we need a special transformer. And then here, all return current using metallic return. So the advantage here, of course, yes, we don't have problem for environment. The disadvantage here, in case one conductor, the power will be interrupted. And then because the voltage polarity here different between positive and negative, there is a DC stress in converter transformer. For this, the design of our transformer will be specific to converter transformer, will be specific to HVDC, while for symmetrical, almost similar with power transformer here. And then the disadvantage here, in case one conductor, the same for symmetrical, the power will be stopped. And then we move to asymmetrical monopole. In asymmetrical monopole, we only have one conductor here, while the current return through ground. For this, we only need one conductor. It will be cheaper. That the losses also a bit cheaper compared to metallic return. And then for this, we also can develop to bipole scheme. The same problem for with metallic return here, the polarity between polarity positive and negative will not be same. At the end, voltage will not be same. Converter will have a DC stress. And then because we are using ground return here, it will be the current going back through ground. At the end, we need ground electrode, and also we have to have a permission, because the ground return sometimes can affect to AC substation on the way back to the substation. So this is mainly, especially we have a problem when the ground return past AC substation where power transformer having very low resistance. And then for bipole, we have also almost same as asymmetrical. We have metallic return. So metallic return here. So what is the difference for bipole? We have two pole here, one pole here, the second pole here. This is actually like combination between asymmetrical monopole. So for metallic return, actually here, for each pole here, we can transfer 50% of the power. So in case any problem for one conductor or one pole, we still can transmit 50% of the power. The disadvantage here, more expensive, because we have more equipment in every substation, almost 2 times in terms of valve and other material. And then the same here, because we are using metallic return. For this, we can see here the polarity between polarity positive and negative. The voltage is not same. At the end, we have a problem. For converter transformer, will have a DC stress here. And then here, return current through conductor. So the losses, because we are using medium voltage, the losses will be high here, because in addition to the losses for high voltage, we also consider the losses in medium voltage. And then the next one, when we are talking about ground return here, there is no medium voltage inside. So we only use ground as a return here. So the advantage same, we have 50% for each pole. In case any problem for one pole or one conductor, we still can transmit 50% of the power. The disadvantage here, we can see still more expensive. There is still DC stress in transformer. And then because we are using the ground return, the same for asymmetrical monopole, we still need permission to because of environmental problem here, because sometimes we have to pass metallic part or AC substation, which still can disturb the substation. And then the next one, we are talking about multi-terminal current, MTDC, multi-terminal high voltage. So here, this is more reliable because we have many sources. Before, we only have 2 stations. Today, if we are talking multi-terminal, can be 3, can be 4, and so on, more reliable. And then bidirectional, because we have fixed voltage. For VSC, we have a fixed voltage. And then the next one, of course, we have, if we don't have problem for asynchronous in the electrical network. The disadvantage here, especially for the substation, the converter station located in the middle can be acting as rectifier or inverter. So for this, we have problem sometimes. The control more complex here. And then the last one, we are talking about back-to-back configuration. Back-to-back configuration, this is actually needed in case we have, let's say, like asynchronous system, and also if we have different frequency between system A and system B. The advantage here, we don't need transmission line because both substation, rectifier and inverter located in the same place or in the same room. And then at the end, because they are located in the same room, we don't need telecommunication, and also of course, converter station will be cheaper. The disadvantage here, the losses will be high because we try to reduce the cost by producing low voltage, meaning the voltage may be about, let's say, like 50 kilo or 100 kV. So at the end, the losses will be high. This is about configuration. And then when we are talking about HVDC, what is HVDC? HVDC actually consisting of submodule. What is submodule? Submodule is collection of IGBT, insulated gate bipolar transistor, diode, and capacitor. And then in order to build the voltage, we call it module. Module consisting of several submodule, which is arranged in series to meet the voltage. Let's say, like if we have 500 kV DC, we have to build a lot of submodule in order to meet 500 kV. In terms of waveform here, VSC converter station produce AC waveform as well, because we have to maintain the voltage in voltage, AC voltage close to AC network. We call it point of common coupling. So today we have three generation of VSC. First generation, it was energized commercially in 1999. So using 2-level converter. And then second generation, we call it 3-level converter. Third generation, modular multi-level converter. This is the configuration of 2-level converter, 3-level converter, and MSC. So when we are talking about 2-level converter, actually we build positive, and when we are doing switching valve, we produce positive voltage, negative voltage. When we are talking about 3-level converter, we switching having three type of voltage: positive voltage, zero, and negative voltage. And then when we are talking about MMC, we are gradually switching the valve submodule. So if we see here, we gradually increase the valve to meet the desired voltage. So we building the voltage gradually here. But for this, we are only switching 2 times, positive, negative, positive, negative. Here, we switching 3 times, positive, zero, negative, negative, positive. This is the difference between 3 configurations. So let's see from circuit point of view. If we are talking about 3-phase 2-level converter, this is configuration of 2-level converter. So at the end, actually the aim to build full wave here, positive, negative, and then back to positive. What we are doing here, yes, here, this is the step. When we switch actually IGBT1, we get positive voltage. And then when we switch to negative, we have to get off IGBT, and then the current will go through diode, meaning the current will commutate the diode. When the commutation process, actually the voltage will go down from positive start from positive going to negative. When the commutation finish, so meaning we conduct the diode 2. So when we conduct the diode 2, the voltage already in negative voltage. And then the same here, when we want to be back to positive voltage, so we get off D2, we commutate the current through IGBT. So for this, the voltage starting going up from 0 going to positive. And then when we have full commutation IGBT, we can conduct IGBT, and then the process we have full voltage here. And this is the situation where actually will be running continuously. So at the end, we have positive, negative, continuously. So here, so because we switch converter positive and negative, at the end, harmonics very high, because we switch the valve with high voltage. High voltage meaning harmonic. We also drive harmonic in this submodule valve. The same here. For 2-level converter, we switch our valve with high frequency, 1 kilo until 2 kilo. At the end, we have high losses here. And for 2-level, actually, when we build the fundamental voltage, we can see in the blue wave. So actually, this is what we don't need. We don't need this one. So for this, we are using pulse wave modulation in order to get a sinusoidal voltage. This is actually our desired voltage. So for this, we use PWM in two-level converter. What is the situation of the two-level? The advantage, very good for low voltage and low power because simple circuit. And then because for low voltage or medium voltage, this is many used in solar panel and wind farm. We will discuss about generating solar panel and wind farm in the next session when we are talking transmission, renewable energy in January. The disadvantage here, because we switch with high frequency, the losses very high. But today we also we can reduce losses if we are using cascade two-level converter. And then here, and also because of we switch in high voltage, we have a problem when we block the fault here. So that's why ability to block to block voltage a problem for two-level. And then again, the last one, because we are switching in the high frequency, at the end we generate low harmonic order, meaning high harmonic, hence we require AC filter. How about three-level? Three-level, this is the three-phase circuit for three-level. The same here, the objective, we want to build the waveform here. The difference with two-level, from positive, we go to 0 before going down to negative, and then from negative going back to 0, and then come back to the original one, meaning positive voltage. The process will be same as two-level converter. The difference only we need 3 steps here. So from positive, 0, and negative. So what happened here? Because we have because we have 3 level at the end, we are still using PWM, but the harmonic will be lower because the voltage, switching voltage between one to the other will be lower. So voltage actually gradually increase. And then what happened, harmonic will be smaller than two-level. Even if we want to build to dump more harmonic, we also can build until 5th or 7th level converter. But the problem here, if we see here, the circuit is very complicated if we are talking about 5 level or 7 level. Here, this is an example comparison between 2 level, 3 level, 5 level, 7 level. We can see here the harmonic will be reduced from 2 to 3, 3 to 5, 5 to 7. So the harmonic will be low in 7 level, but the circuit will be very complicated here. The advantage here, switching process will be three stages. So the pressure for the equipment will be lower than 2 level, because for 2 level, we switch plus and negative in very short time. At the end, we have stress on isolation equipment, but here less because we have a 0 voltage in between. And then disadvantage here, we need more number of conductor. And then here we can see here the more complex. And then same here, the IGBT will have different stress here. So this is if we see here the stress for outer valve reactor for IGBT 1 and 4 here, 1 and 4 here will be more than 2 and 3. So for 1, we are doing conduction and switching, and then for inner valve converter arm, we only doing conduction process here. And then at the end, cost will be more expensive because we need more valve here. And then we move to MMC. And MMC, we have 2 types of MMC. We have half bridge and full bridge. So here, example of three-piece circuit for half bridge. So half bridge consisting of many submodules, depend on the voltage. let's say I zoom only one submodule here. This is one submodule. So one submodule here actually consisting of two arms here. And also here for MMC, half bridge, we are only able to produce unipolar. What is unipolar? We only produce one side of voltage. Let's say for polarity positive, we only build positive. And then in order to build negative voltage, we have to use negative polarity. So this is for MMC. The process again same. So if we are, this is example, I zoom here 5 submodule, but actually in reality, submodule can be 100 because every switching normally the discrete voltage increment roughly 2 kilovolt. So imagine if we have 500 kV, we have 250 times switching in order to meet 500 kV. So this is example I put 4, 5 submodule. So when we switch here, we are going to hear the same B. We got this until we pick on the highest voltage in the submodule E. But in reality can be 100. But this is only simulation for 5 submodule. Depend on the voltage we build in phase C. And then the component here, if we see here, submodule, we have capacitor, we have resistor, we have IGBT, diode, and then diode here. And then this is bypass. In case we have problem, we can bypass in order not to break or to damage all equipment here. So the definition here, when we insert, we call it inserted, bypass, and block. Inserted when we want to build, bypass if IGBT not in operation, and then the block when we block IGBT not working, but the diode still working. The advantage here, because we build the discrete voltage, let's say like only 2 kV per switching, at the end the harmonic very low. So since the harmonic very low, we can dump using control. At the end, because we can dump the harmonic also very small. In case any harmonic appear, mostly high order harmonic, so we can dump through control. At the end, most of the time for MC topology, we don't need AC filter. And then here, every time we switch in very low voltage, we can say roughly 2 kV, can depend on the design. And then also the same here, switching in low frequency, at the end, losses will be low here. This disadvantage here for medium volt, for high half bridge, because we have only monopole, unipolar voltage here. In case any DC fault, the DC fault recovery will be long. Why? Because when we block the IGBT, actually the current still go through, disconnect the diode. And why we need 1.5 seconds? This is because we need circuit breaker to stop the power. This is the disadvantage of half bridge, meaning the fault recovery will be longer, depend on how speed will be AC circuit breaker working. And then the other disadvantage, we need more submodule because we build the power with discrete voltage here. So we need, every time we need submodule and then increment only 2 kV. So imagine if we have 500 kV, we have to switch more than 250 times. This is example when we are talking about cascade to level. Cascade to level, actually the principle almost same as MMC here. So for this switching in low frequency, at the end, the losses will be lower. And then when we are going to MMC, the same here, the configuration, this is three-phase circuit. So if I zoom here, submodule, every submodule consisting of 4 arms, 1, 2, 3, 4. We have 4 arms instead of 2. because we have 4 amp, we are able to build bipolar. What is bipolar? Here, every submodule, we can build positive and negative voltage. So positive here, and then negative here. So because how the process going, actually, we have 4 steps here. When we build, again here, if we make simulation for 5 submodule, so when we want to reach this one, we're switching step 1 from 0 voltage until full voltage. And then we are using negative current here to have a voltage down from positive become 0. And then the same here, when we are decreasing to get negative, we are using negative current. We are using positive current, and then the voltage will going from 0 to negative. And then again, the last one, we are using negative current in order to increase the power from negative to voltage to positive voltage. What is the advantage? Because we build bipolar, so actually we have we can build AC voltage and combination between AC and DC components. So at the end, in case any fault in DC, the fault recovery will be very slow because we can control the DC. We don't need circuit breaker. At the end, imagine here, this is one example. We can isolate the power only in 160 millisecond. But this is once again only rule of thumb, not depend on the design here. And here, the same for half bridge, because we generate discrete voltage. At the end, the harmonics very, very low. The disadvantage here, because we have more equipment, we have more losses. And then because we have more equipment, the valve or converter will be more more expensive. And then the end, because we need more component here, of course, the circuit will be more complex compared to half bridge. Now the next one, we are talking about converter valve and network. So imagine here, this is the scheme here. This is high. This is converter station. This is AC system. So if I put here, when we build here the voltage, if we, okay, this is equivalent to circuit like this here. This is for converter station. This is AC system. When we see here, there is a problem, not problem. There is a phase angle between voltage here, between converter and AC system. So we call it DC. So actually, this is where actually we play when we are talking about active or reactive power exchange between converter station and AC system. So actually, we build the voltage in this until this point, and then this is AC point. And when we are talking about the exchange power, we can see what will be superior one against the other. Here, example of PQ diagram. So if you see here, PQ diagram, when we are talking about inverter, we are talking about the diagram 1 and 4. So what is 1 and 4 here? When we have, for instance, 1 here, if we have, we produce valve more than AC system, actually we are in capacitive mode. The same here, when our valve lower than AC system, we only we are in inductive mode. This is the scheme here. And then this is the formula when we transfer the power. And then the active power can be controlled by phase angle here. And then for AC substation, for AC reactive power here, the definition, if AC system greater than the voltage created by valve, so meaning the reactive power will be supplied to converter. The same here, when VSC, when voltage AC system lower than voltage converter, So converter can transfer the power, reactive power to AC system. When we have balance between AC voltage and converter, there is no exchange power. So this is the philosophy, the exchange power between converter station and AC substation or AC system. So when we are talking about converter station, we are talking about AC substation. So actually AC substation here, same as standard AC. So we have all component here, circuit breaker, disconnector, earthing switch, voltage transformer, current transformer, surge arrestor, power transformer, control, all in AC substation. And then when we are talking about valve here, in valve hall, we have valve converter, we have cooling pipe here for to cool the submodule. And then we have disconnector, okay, and earthing switch. We also have wall bushing and DC wall bushing. Valve here, because of electric components, very sensitive. There are two methods of installation. We can install valve on the floor. This is mainly if we have low seismic. And then we also can hang valve here in the ceiling if we have high seismic. But once again, this is rule of thumb, depend on the design of the supplier here. So when we are talking about AC wall bushing, this is example of AC wall bushing. What is AC wall bushing? This is valve. So conductor to connect to transformer, converter transformer, we call it AC wall bushing. The same here, DC wall bushing is connection on the other side, if here AC, and then here on the other side we have DC. The connection between conductor, connection between valve to a DC substation, we call DC wall bushing. This is example connection from valve to DC smoothing reactor, we use DC wall bushing. For DC substation, same, we have almost same as AC substation. All component here, we have AC, but for this we have DC components, disconnector on earthing seat, voltage divider, and so on. The difference here, the main difference with AC, we have converter transformer here, we have valve reactor, and then we have DC smoothing reactor. But all here, you see, having DC voltage. So when we are talking about the layout, this is example of VSC having 320 kV with the rating between 600 to 1000 megawatt with indoor DC station. This is example the size of AC station. This is the layout of converter station. This is a pair of converter station. And then we have also valve here for positive polarity. We have valve for negative polarity. We have valve reactor and smoothing reactor. And then at the end, we have DC substation. So this is once again typical indoor substation. Of course, the design or the size will be depend on the design and requirement here. For control station, chapter 5 here. So what is converter station? Converter station, control converter station is to coordinate operation of converter station. So set of order operation converter station, and then to set current balance between pole or between pole and monopole for bipole system. So we need more control equipment for DC. And then all control using protocol standard, for instance, like IEC 06X70-5-104 or DNP3. And then when we are talking about control, we are talking about hierarchy. The highest hierarchy will be load dispatching center. This is the highest hierarchy. Usually load dispatching center, not in converter station, maybe a bit far, but depend on the site. Sometimes can be close, but most of time quite far. And then we also have a control converter station here. And then the last one, we have control converter valve. So this is the example. This is once again typical hierarchy of control station for in VSC. This is example of how many control we need for VSC. Yeah, I have listed here 14 here. We have emergency, AC current control, DC current, and so on. So we have 14, and then once again depend on requirement. And one good thing, one advantage of VSC, we have black start operation and islanded control. This is the good point of VSC here. And then the last topic, we are talking about protection here. What is protection? Protection actually to protect installation, to isolate fault equipment, and then to protect the healthy equipment in order not to damage when caused by fault. When we are talking about protection, we are also talking about human life. The aim also to keep operators safe and then to avoid fire hazard in substation. So this is example of control and protection. Cubicle, we have protection main 1, protection main 2, control, and then this is to control a valve here. So when we are talking about protection, we are talking about protection zone. The same for AC. Actually, in HVDC, this is typical protection zone here, I mentioned here. So for instance, we can have zone 1 for only to protect AC, and then zone 2 here to protect converter station, zone 3 to protect converter transformer, and then zone 4 to protect only valve, and zone 5 to protect all overhead line or cable. Once again, this is only typical zone protection. Can be 5 zone, can be 6 zone, depend on the design here. This is only typical. So in terms of block diagram and protection, so here for protection, actually protection in VSC quite sophisticated. In main protection, actually, if we see here, so we have equipment shall be protecting at least one protection zone, and then zone protection actually overlap each other, and then faulty equipment should be tripped and isolated as quick as possible. In case of redundant here, actually the function will be same as main protection here. In case redundant, actually should be minimum disturbance time when we switch from main protection to protection redundant. And all fault within converter station actually should be protected by 2 protection. We call it main and backup, main and backup, main and backup. Every time we have main and backup. So this is typical, once again, typical, not really reflected to any other design. So this is typical. When we are talking about protection valve here, this is one example I take here. When we are talking about protection converter valve here, let's say we have main protection here over current, valve over current, and then we have backup protection differential here, and then we have redundant, as we mentioned here, we have also redundant here. So this is example how the protection working in HVDC scheme. And then the next one, how we see a fault on DC transmission line. In DC transmission line, when so actually always circuit breaker to isolate the fault here. When trip signal is sent to AC breaker here, when we trip actually at the same time, the breaker failure protection signal will be sent to circuit breaker 2 and 3 here. So in case, so once again, normally in normal condition, in case any fault here, circuit breaker 1 will stop the power. But in case this one will be failed, because we already send breaker failure protection signal to backup equipment here, CB1 and CB2. So if this one is failed, actually the next one, the circuit breaker 2 and 3 will be closed, will be open. So by this, the fault will be isolated. And then how when we are talking about recovery, diagram, how it works. Actually, in VSC, when we have line fault here, we have detection time. After detection time here, we detect any fault, our valve will be blocked. When valve blocked, actually, as we say here, the circuit breaker will be open, and then the same time, AC resistor will be also open. And then when they open, because this is a temporary, once again, if any temporary, we could not close circuit breaker 1 in case temporary fault. Depend on circuit breaker ionization, and also depend on how long time DC transmission will discharge energy. Once this one solved, we can close circuit breaker, and then we can also close pre-existing resistor, and then the last one we deblock will deblock our valve, and then the power will be transferred. This is the process for recovery diagram. I think this is what I want to share to all of you for this today. So once again, I only review 6 chapters out of 11 chapters here. So so thank you very much for your all attention here. So in case any question, I try to answer as much as possible. In case I could not answer, I will come back to you, because we still have session in January to review how VSC engineering works, how you do testing in factory, the electric test and field test, and also how you compare between AC and DC in terms of technical and price, and then we can see the reference. So I think I cover the topic for this evening. Thank you very much for your attention.
And wonderful, thank you very, very much, Terklin. You've got a very lot to cover, and I think your books are going to be extremely interesting. And we are getting comments that say thank you very much for a concise presentation. So yes, it's absolutely brilliant. And also, I know that this is actually being broadcast from Stafford, Northwest Midlands, and Stafford is a bit of a hotspot for high voltage, etc. Particularly GE is a large employer here as well. So Terklin, thank you very much for your time. But hopefully you've still got a bit of time left over, because we've got quite a few questions that are coming in. And I just want to remind everybody, if you do want to ask questions, do use the Q&A rather than the chat box, because we can actually download the Q&A and we can move them to answered and everything rather than the chat. So if you put some questions in the chat, just copy and paste it into the Q&A, and then we'll take it from there. Just to remind everybody, we do have a YouTube channel, and this is being recorded, and it will be played and live on the YouTube channel probably within about a week. So I've noticed that we've got a few subscribers already. The link is in the chat, and thank you for those of you who subscribed already. That's wonderful. So once again, I've just given you a little bit of a rest of your voice there, Terklin, and hopefully you've had time to have a bit of a drink. And I'd just like to pass over to Amelia, who will then just field some of the questions, and she will verbally ask you then, Terklin, so you don't have to read things, and then you can verbally answer the questions as well. So over to you, Amelia.
Thank you, Sam. And thank you everyone for staying and listening. We still have majority of the participants with us, which is good. There are some questions that are in the Q&A session. What I will do is I will read out some questions to Terklin, and Terklin will try and answer the questions. As Sam mentioned, if there are any questions that cannot be answered tonight, we will download them and will endeavor to answer them on the forum. Okay, so Terklin, are you ready? If you're ready, you can put your video on, and I can ask you the first question.
Okay, I'm ready.
Okay, so the first question is, DC transmission power losses are relatively small. but taking into account also the losses on AC to DC and DC to AC conversion efficiency.
Yes, please.
Yeah. So it's there is a question mark at the end. So I think they're asking, does it take, so when you say DC transmission power losses are relatively small, I think their question is that taking into consideration the losses on AC to DC and DC to AC conversion and efficiency as well?
Thank you very much for this question. Actually, when I mentioned here lost electricity, this is for all. When we are talking about AC here, so all the losses in AC substation plus transmission line. And when we are talking about VSC here, the same. We combine all the losses in AC substation. So if we see here, we are combined between, I will show you here. So when we are talking about the losses here, so for AC actually only talking about AC substation plus transmission line. But when we are talking about DC, we also combine here the losses of AC substation, the losses of valve here, valve reactor, smoothing reactor, and converter valve, plus the losses of transmission line. So here we are talking about apple-to-apple comparison, meaning the total losses of AC substation plus transmission line here, the total losses of AC substation, converter station, and DC transmission line, and at the end the losses only, in the total, by rule of the thumb, the losses of DC will be 20 to 30% lower than AC, apple-to-apple comparison. So we will review more in next session, January actually. But what I want to say here, by rule of the thumb, DC always depend on the transmission and power. By rule of the thumb, DC always about 20% or 30% lower than AC in terms of global losses.
Thank you, Terklin. There are a few people who are still asking whether they can download slides. Please be aware that we were recording the presentation, and it will be on our YouTube channel. I think Sam has shared the link for that. If he hasn't, please do search for IET Northwest Midlands local network, and within maybe a week or so you should see something there. Okay, so we move on to the next question. The next question is on bipole. Are the return currents for the two poles of the bipole in opposite directions such that there is a net current only when there is an imbalance between the two poles?
Yeah, so what is the question there? Yeah.
Okay, so in this topology, the one you're sharing, they're asking, are the return currents for the two poles of the bipole in opposite directions?
Actually, ideally will be balanced, but there is, of course, sometimes the difference between sending and return back. So there is a small current difference, but ideally should be zero.
Okay, thank you. Okay, asymmetric bipole. The question is on asymmetric bipole. And the question was...
asymmetrical, there is no asymmetrical bipole, asymmetrical monopole.
Okay. The question here was, what causes the high cost and problems in return path? So maybe they just got the title wrong. Perhaps it was, I don't know whether they wanted to say asymmetric monopole.
Yeah, actually, maybe I just try to clarify. For asymmetrical monopole, we have two types. One with ground return. So for this, we only have one high voltage. We don't have any conductor here. We use ground. But the problem for ground, for return current, sometimes when you pass, let's say like metallic or AC substation, can disturb AC substation or metallic, let's say like corrosion and so on. This is for ground return. And then for metallic return, actually there is no problem because you are using medium voltage for return current, but at the end, it will be additional cost because we have to buy medium voltage conductor, plus we also have losses for medium voltage. I think I try to answer what he want to say here. The difference here, we have additional cost for medium voltage plus additional losses because of medium voltage. But here we don't have losses or cable for the second conductor, but we have to have permission because when we have return current, we will pass metallic equipment or AC substation can disturb AC substation or can disturb metallic, for instance, like pipe. It can make, let's say, like easy for corrosion for metallic part.
Thank you, Terklin. We've answered a few questions so far. Just to check with you, are you okay to continue answering questions?
Yeah, I'm still okay for a few more minutes. Yes.
Yeah, okay. So we do have a question here. What does the PIR do?
Okay. Yeah. Yes, actually here I already mentioned here. This is PIR. So PIR here to limit, actually here I make already definition to limit voltage when we start, actually when we energize, actually, you know, for VSC, actually, especially for onshore, very crucial here. We always energize the converter station here when we are working on commissioning. When we want to start operation, we energize through PIR. What happened here, actually, the disturbance can happen for this, the resistor here to dump, I mean to reduce the voltage increase occur when you just start. Actually, PR pre-inserted resistor here only working when you start the converter station, when you start operation. So this is actually will be a crucial time because the disturbance can be happen. For this, we need something to absorb the voltage increase.
Thank you. Okay. The other question that is here is, what are the causes of higher AC transmission losses?
Oh, yes. Actually, I already mentioned here. Actually, if we see here, this is example AC here. What happened for AC? For AC, actually, we need three phases here, A, B, and C. So imagine here, if we have 1,000 kilometers with certain number of resistance, so we have losses for three conductor here, 3 times here. While for DC, you only need 2 here, 2 conductor here. This is one, so that's why here the different only, mainly we can see number of conductor, and also here the resistance. Resistance here for AC higher than DC for the same voltage. Why? Because for AC actually we have the effect, what we call it skin effect. Skin effect also will give more losses on conductor. While for DC, we don't have a problem for skin effect because the current distributed to all conductor. So that's why in terms of number conductor, we have more for AC compared to DC. And also in terms of skin effect, for AC, we have skin effect. While for DC, we don't have skin effect for conductor. So this is when we compare actually in the next session, January, we can see the difference actually mainly in transmission losses, where actually the transmission losses for AC much more higher than transmission losses of the DC here, much lower than AC here.
Thank you.
So I don't know if it is already answered. So once again, if I want to sum up, number of conductor we have more for AC, and then the skin effect we have skin effect in AC, while for DC we don't have, and the number of conductor for DC smaller than number of conductor in AC. So in total, if we compare apple to apple, the losses will be much different.
Thank you, Terklin. There are still a few questions left. Are you in a position to answer them? I mean, there is the option to also download these and answer them and then put them on the forum.
Maybe one or two more questions, yeah, because I bet this we have to limit, and then in case any question, we will answer the question, and the same, we will have another session in January. So you can part the question, and then we can ask during the next session.
Okay. So here we've got the question is, in terms of public health and safety, it is thought that the proximity to HVAC systems can be dangerous. Is this the same for HVDC?
This is correct. So actually, there is a research here, because today, when we are talking about corona and noise interference, actually the phenomena will be different. For instance, like in transmission line, for instance, during, let's say, like during raining, actually even the noise interference for DC lower than AC, and then the reverse for AC. So what I want to say here, both AC and DC, actually, they have a problem for noise interference, or also for health and safety. We could not say DC worse than AC. Yeah. This is a very blunt statement here. But of course, there are some research to compare the impact of having AC and DC, yeah, in the transmission line.
Thank you. Okay. So you said you've got room for one more question.
One more question, please.
Okay. Right. There is quite interest in PIR.
In PIR, yeah.
Yeah. But I'm not sure if I understand the question. Could point of wave switching be used instead of PIR?
This is a good question. We will answer this offline. Yeah. Yes, we will answer this offline. Yeah.
Okay.
Okay. You okay, Amelia? That you've done extremely well in fielding those questions. Well done, and it's really debated a lot of good chat here. And I'd just like to remind everybody that we do have a forum, and the link is in the chat box, and that's right towards the top of the chat box. And I've just been reminded that you don't need to be an IET member to access our website and our forum. And in fact, you can sign up as a guest, and then you can download the CPD certificates that way. So you don't have to actually be a member. And I see we've got quite a few subscribers onto YouTube, so they are all waiting with bated breath for the YouTube recording of this, Terklin. So obviously you've kept people very interested in this. So I'll just remind you that there will be a forum for this, so you can take this further, and Terklin will then follow up on the forum. Some of the questions, Terklin, are about the slides and the availability of the slides. So that might be something that you might want to consider, although it will be recorded onto YouTube. So I don't know if you have any thoughts on the availability of the slides, or if you have your own website even as well.
Yes, if this is the question, yes, of course, I am ready to share the slide in PDF file in the forum. Yeah.
Okay, so we will follow that up, and we have access to putting slides up there onto the IET Northwest Midlands website. Again, if you can't find the links, they are towards the top of the chat box. So thank you very much. Okay, so that just leads me to thank you very much again, Terklin, to make this an absolutely excellent and really well attended event. It's been absolutely buzzing with chats and it's been buzzing with questions. Your presentation, I must admit, I don't really understand high voltage electricity, but it still held me captive right to the very end. So I'm sure that your books, when they are translated into English, and I'm sure you'll mention these on the forum as well, of where people can buy your books from. So that would be great if you can look at that as well. And as I said, the links are within the chat. Okay, everybody. So thank you very much. And Terklin, you are getting lots of, I don't know if you can see the chat box, but you are getting lots of thanks from everybody. One comment, names are not written on the CPD certificate. That's correct. You fill in your own name. We can't make individual certificates for everybody. So we trust that you will download it and then you fill it in with the details of the event and then put that into your portfolio of evidence. So Terklin, I don't know, can you see all the thank yous that are coming in?
Yes, I see. Thank you very much for all audiences, because for me, this is also a good time to share with everybody here. So also to the committee, thank you very much to give me opportunity to deliver presentation here. I'm really pleased to receive any question and then of course to share any other information to all audiences. Thank
you very much. So I can hear fireworks going around outside. It's bonfire night and it's not stopped people setting off fireworks. So you've done very well in keeping people entertained as well with your presentation. So if we can take the rest of the questions will be held on the forum and then we'll take it offline from there. And also just to remind you that Terklin will be presenting the second half of this. And I think, Amelia, can you just remind us of the date? Is it the 29th of January for the next one?
Yes, the 29th of January will be for the last 5 topics of this book. And then hopefully next year we look to have maybe a couple of presentations on LCC. Thank you.
Wonderful. Okay, so have a look on our website. I don't think we've quite made it live yet, so you can't quite join for the 29th of January, but we will do it very shortly. We've only decided on the date recently because originally I think we had about 250 slides with this, and then we said, no, let's split this over several events. So we will put that online within a few days. So thank you again, Terklin. Well done, Amelia, with the questions. And thank you, everybody, for your wonderful questions and for coming on board. And I wish you all good night.
Thank you.
Thank you.
Thank you.
Good night. Bye-bye.
Bye.